Good afternoon, everyone. And first of all, many thanks to Barbara and Alex for inviting me. I'm very happy to be here. And what I want to present to you today is not really one finished story, but more a collection of observations and ideas we've had in our group in Oslo. And as such, this is not only my work, but a lot has been done by Ariane Petley-Regan, who is a PhD student in Oslo, Björn Jamtveit and Håkon Austrheim, who are metamorphic petrologists, and François Renard from rock mechanics. We are now, with this presentation, going from this very large-scale subducting slabs to basically micro to nanometer scale observations. And the reason that I think that microstructures are so important is that we can learn a lot from them about especially the early stages of sliding, and because of that, also maybe about the origin of earthquakes. So I'm working on natural rocks, and the most common indicator we have for seismic faulting in rocks are, of course, pseudotecholites. Pseudotecholites are dark, fine-grained, or glassy fault rocks, commonly interpreted to form during seismic slip. This is an example of a pseudotecholite, the dark material here, which is in a rock from the Bergen Arcs, similar to ones I'm going to talk about later. Regarding the formation of pseudotecholites, there are two end-member mechanisms, comminution and melting. And comminution can actually be seen as a prerequisite to frictional melting. So pseudotecholites are great to identify earthquakes in rocks, but there is one big problem with them, and that they are very unstable. They are fine-grained or glassy, so obviously they are very susceptible to deformation, recrystallization, or alteration, which led Kirkpatrick and Roy to call them disappearing ink. So what are the best options? What kind of pseudotecholites should we study to find out something about the origin of earthquakes? What other indicators are there that could help us to identify fossil earthquakes? And one thing that we have focused on in particular is the wall rock to pseudotecholites. Because even if the pseudotecholites are gone, the wall rock might still be there. And a lot can happen to the wall rock too. Wall rock minerals can be fragmented. They can react, the wall rock can be infiltrated by melts or by aqueous fluids. So most of my talk, as I said, will be focused on microstructures, but I will actually start with some field scale observations and then zoom in and further and further. And the example on which I'm going to do that is related to dehydration-induced seismicity in partially hydrated peridotites, which I hope might be of interest to some people in this community. The field observations we start with is the scaling behavior of fault offsets. These are ophiolitic peridotites with these dark chromite bands, which are offset along numerous faults, which are located in the centers of thin veins. And we measured the displacement on these faults, on over 500 faults in the field, and calculated their distribution. We then compared this distribution to what would be expected from the Gutenberg-Richter law. I know, of course, that the Gutenberg-Richter law concerns earthquake magnitudes and not displacements, but there is an empirical relationship between the two parameters, so we can roughly relate the two. Though we can fit a power law to our data here is already kind of a nice indicator that we might have had earthquakes here. I'm aware that the fit is very bad in low and high displacements, that can easily be explained by difficulties in measuring these kind of displacements in the field. It's quite hard to see millimeter scale displacements, and meter scale or tens of meter scale displacements might not be visible because of later structures. Anyway, we can then from this power law exponent that we have here, we can calculate a B value. In this case, we get 1.4. And this actually fits perfectly because B values that are slightly higher than the global average of 1 are actually typical for regions undergoing dehydration reactions. Right, so now I of course have to show you some microstructures of these rocks as well. As I mentioned before, the faults are located in the centers of thin veins. So in this case, a fault would be here. You can't see it because there is no chromite band as a marker, but I hope you believe me that there's a fault here in the center. The host rock is a dunite, so it's almost pure olivine, and this vein here consists of olivine as well. But it has quite different properties to the olivine surrounding it. So the olivine in the veins is characterized by magnetite inclusions, heterogeneous compositions with high forsterite values, and delta 18O values different from those of the host. And these factors all point to deserpentinization as the origin of these olivines, meaning that there used to be olivine where the veins are today that was dehydrated. No, I'm sorry, there used to be serpentine where the veins are today that was dehydrated to olivine as the temperatures rose. If we want to learn more about the processes during deserpentinization, we can look at an area like this using electron backscatter diffraction. So this is an olivine orientation map with inverse pole figure color coding. Down here, you have the wall rock. This is the outer part of the veins, which is very coarse grain. This is the inner part of the vein, and the fault would be here. And so up here, we would again have a fine grain area, the coarse grain outer area of the veins, and then another wall rock at the top. Right, so you see that the host rock is kind of fine grain, slightly porphyroclastic. The inner part of the veins is very fine grained as well, but the outer part is coarse grained and is characterized by kind of peculiar straight olivine grain boundaries that can be followed along several grains. For now, I'm calling this a brick-like olivine microstructure. And something that's very striking is that the crystallographic preferred orientation of the olivine in all three areas looks exactly the same. Do not let it confuse you that the preferred orientation seems to be kind of parallel to the orientation of the vein. There are veins that are perpendicular to that, and they all show the exact same crystallographic preferred orientation. So what does that mean? Did all three areas experience exactly the same? Maybe at some point. But obviously something else must have happened to explain their different structures and compositions. We can learn a bit more about that by looking at the, yes, I mentioned that, it's a constant crystallographic preferred orientation. And we can learn more about that by looking at the internal misorientations. So these are internal misorientation maps of single olivine crystals that are representative for each area. This is the host rock, this is the coarse grained outer part of the vein, fine grained inner part of the vein. And you see that in the host rock, this is a porphyroclast from the host rock, you have nice, straight, parallel subgrain boundaries and quite high internal misorientations. In the outer part of the veins, the misorientations are quite low, and the subgrains are more patchy, not as parallel as here. And then in the inner part of the veins, the grains are strongly fragmented. That's why we have all these gaps here. And we have higher misorientations again. These are the misorientation angles. We can also have a look at the misorientation axes, which you see here. The axes around which the crystal lattices of the subgrains are rotated with respect to each other. In the host rock, there is a strong preference for certain misorientation axes, but the distributions in the veins is almost random. So if you look at the scale here, these are almost uniform distributions. From this, we can see that different kinds of deformation affected these areas. Only the host rock experienced significant crystal plastic deformation, whereas the veins record much lower temperature deformation. So this means that the CPO, the crystallographic preferred orientation of the olivine in the veins, was inherited from a precursor that looked like the host rock that we have today. And how that could work, I'll try to explain with this sketch. So we start with a dunite that has been affected by crystal plastic deformation at high temperatures and obtained a porphyroclastic fabric. This dunite was then fractured. You have to imagine as a background a porphyroclastic dunite. These are two chromite grains, and everything is cut by a set of fractures. Along these fractures, fluids infiltrate the rock, which is hydrated to serpentine around the fractures. Now, when the temperatures rise and dehydration starts, where would the new olivine be most likely to form? The most favorable nucleation sites would be the small olivine relics that survived the hydration, like the olivines that we often see in the centers of a serpentine mesh structure. And if we imagine that olivine grows epitaxially on those small relics, the newly grown olivine in the vein is going to have the exact same crystallographic preferred orientation as the host rock, but without the internal misorientations that would point to crystalloplastic deformation. Now, if dehydration continues and more serpentine reacts to olivine, the increase in pore fluid pressure will lead to embrittlement, and some of the faults along which the rock was serpentinized in the beginning were reactivated as faults, and additional sliding happened. In the course of this event, the olivine grains, the newly formed prograde olivine grains next to the fault plane were fragmented, but the strain was extremely localized on these discrete fault planes. That means that the crystallographic preferred orientation could be preserved even in this stage. This is something that's very similar to pulverization that has been described from shallow faults, and I'll talk a little bit more about that later. So we hopefully see that in this kind of setting, dehydration-induced faulting is possible. But of course, we have a very special case here. We have isolated serpentine veins in a host of strong olivine. And with that, I can kind of support a little bit what Nadej said yesterday, that the dehydration of a mixture of serpentine and olivine is much more likely to lead to seismic events than the dehydration of weak, pure serpentinite. So as a little summary regarding this part of my presentation, I'd like to say that the dehydration of partially serpentinized dunites from this ophiolite complex led to the growth of prograde brick-like olivine and to dehydration embrittlement. And the strong strain localization, the pulverization of olivine, and a Gutenberg-Richter B-value of 1.4 all point to unstable sliding. And therefore, I conclude that arguments for or against deserpentinization-induced seismicity really should include the amount and particularly the distribution of serpentine. So this was a field example of a case where we think we had seismic faulting, but we did not have a pseudotechelite. Now we'll finally get to the cases where we do have pseudotechelites, so we know that there was frictional melting. When we want to study the microstructures of the pseudotechelite, we should make sure to choose one that actually shows us what we want to see. The microstructures formed during or maybe right before the earthquake. So what kind of pseudotechelites should we look for? In that regard, we basically stumbled upon kind of an interesting observation when we looked at ultramafic pseudotechelites from Alpine Corsica. So this is a dunite, an olivine ridge rock again, with a pseudotechelite here in the corner. And if we look at that pseudotechelite using transmission electron microscopy, we see that the olivine in the pseudotechelite is extremely rich in dislocations. It has dislocation densities of in the order of 10 to the 14 per square meter, whereas pyroxene here is almost dislocation-free. This tells us two things. The first thing is that we had incomplete melting. So I think the olivine of the wall rock basically was fragmented and incorporated into the pseudotechelite, whereas pyroxene melted and then crystallized again. The other thing we see is that recovery was extremely limited. And this latter point is what surprised us a lot. We would have expected to see at least a little bit of subgrain formation in these olivines, but there's nothing. These dislocations are a complete mess. Then we thought this pseudotechelite is very thin. How does the temperature increase associated with sliding, well, how long does this temperature increase associated with sliding actually last? As it turns out, for our 1 millimeter thick pseudotechelite, the temperature will be back down to ambient temperature after basically a few seconds. Unfortunately, I have not been able to find annealing rates for olivine as a function of temperature, and this would be really nice to compare this very rough model to that. So if anyone has information on annealing rates of olivine, I would be very grateful to hear about it. But in any case, it seems that in a thin pseudotechelite, cooling might be so quick that significant annealing is not possible. So we might actually want to focus on thin pseudotechelites that are quite hard to discover in the field instead of their larger, more spectacular big brothers. But no matter how nice the pseudotechelites are initially and how many structures they preserve, a lot can happen to them after their formation. In particular, ductile shear zones like to nucleate on planar compositional or structural precursors, such as pseudotechelites, which leads to a myelinitization of the pseudotechelites. the reactivation of pseudotachelites as shear zones has been described by Luca Mennigan and others from Lofoten in northern Norway, where they distinguish pristine pseudotachelites, like here, which actually contain microlights and maybe even glass, recrystallized pseudotachelites, and myelonitized pseudotachelites, such as this one. And obviously, most, if not all, of the microstructures that formed before or during the seismic event will be gone in this case. Here we have an example of a slightly myelonitized pseudotachelite in a backscatter image. This is also from Lofoten, where we sampled this summer. You see here garnets with some relic dendritic structures, which is very typical for pseudotachelites. You have a matrix of plagioclase and pyroxene, and you have these plagioclase clasts here. These clasts are obviously elongated, they've been stretched out, and the plagioclase grains in them have a preferred orientation that is parallel to the orientation of the pseudotachelite. The wall rock next to this pseudotachelite, however, looks quite different. Here the plagioclase is also somewhat fragmented, but it's not sheared. You might see this a little bit better in the next image. This is a false colored, forward scattered electron image, so this basically shows orientation contrast. And you see that this is kind of a nice plagioclase, but something is obviously going on here and here. And unfortunately, I just got this data yesterday, so I haven't made the plots yet, but I saw that in this case, the plagioclase does not have a crystallographic preferred orientation parallel to the pseudotachelite, but it actually has the same orientation as the host. So there's not a lot of shearing going on. So pseudotachelites, of course, represent weaknesses when it comes to ductile deformation. And further deformation is often going to be localized in the pseudotachelites. But seismic microstructures might actually survive in the wall rock, which is why we like to focus there. So next I will go in a little bit more detail on another example, which is from the Bergen Arcs. We look at the granulite wall rock of pseudotachelites. This is a geological map of the island of Holsnøy in the Bergen Arcs in western Norway, where we have here the location of pseudotachelites. There are actually quite a few more now, and the distribution of eclogite shear zones. The pseudotachelites have been linked to the shear zones, and I believe that Marco might talk a little bit more about that later. For me, the only thing that's important at the moment is that these pseudotachelite also formed under eclogite facies conditions. So we have somewhat constrained their formation depth and can say that these are intermediate depth earthquakes. So we studied granulite facies anorthosite with eclogite facies pseudotachelites. Yeah, I should mention these are anorthosites, so this is from the continental crust, not from the oceanic crust. In particular, we looked at two garnets here. One garnet here, directly next to the pseudotachelite, actually cut by the pseudotachelite, and one garnet that's approximately 2 millimeters away from the pseudotachelite. Here we have backscatter images of the two garnets, and you can see that both of them aren't really single crystals anymore, but they have been fractured and fragmented. Nevertheless, they do not appear to be strongly sheared, but still kept their original shape. The intense fragmentation you can see especially well in this map. This is an orientation map. This is the garnet right next to the pseudotachelite, which is up here. And the grain boundaries are here in black. So you see that instead of one single crystal, we now have hundreds of new grains. This is a map of the grain internal misorientations of the garnet a couple of millimeters away from the pseudotachelite. In blue is what I consider the relatively undeformed part of the map. In pink, the fragmented, deformed part of the grain. And on these pole figures, you see the orientation of this fragmented part, and you see that there's a strong crystallographic preferred orientation, although we have lots and lots of grains, and this orientation coincides with the orientation of this relatively undeformed part, which is here plotted as the black dots. So we see that we have a strong fragmentation without shearing. And a fragmentation without shearing is, in shallow earthquake literature, defined as pulverization. However, there is one more thing to this definition, and that is that the pulverized rock actually falls apart in your hands when you sample it. This is obviously not the case here, but that's not so surprising because we are at a much higher confining pressure, and we also have more of an opportunity for annealing afterwards. You might, of course, ask, why do I think this is pulverization, fragmentation? Why don't I think this is just recrystallization? Why should this be even related to the earthquake? Well, the garnets were not only fragmented, but they were also infiltrated by a melt. These are two FIB tomography volumes with a width of 20 micrometers. First of all, you see that there are a lot of inclusions. So these are the inclusions in the garnet. There are 7% inclusions in the garnet next to the pseudotechlide, 2.5% in the garnet a little bit further away. And especially here you can see that the inclusions are very often flat or L-shaped, which indicates that they grew along the grain boundaries of the garnet. This is something you can also see in this TEM image. Most of it is garnet, but we have corundum, apatite, sulfides, and pores along the grain boundary here, and we have melt. We can clearly identify this as melt because it's clearly non-crystalline in the transmission electron microscope, and it has a vast variety of different elements, including a lot of incompatible elements. So from this we know that the grain boundaries have to have been there before the frictional melt formed and infiltrated this rock. And now the question is, of course, how exactly did this pulverization or fragmentation happen? Was it a purely brittle process, or was the movement of dislocations involved? We can find out something about that by looking at these TEM images. This, again, is from the garnet next to the pseudotechlide. This is from the one further away. This is the relatively undeformed part. This is the fragmented part. And you see that you have a high but variable dislocation density in the fragmented part. There are some structures that look like subgrains might develop, but there's very little of it. So what we see is crystalloplastic deformation with incomplete recovery. Something else I should mention is that there is not a single slip system in garnet responsible for this, but a multitude of different slip systems. So we think this might actually also be indicative of earthquake deformation, that basically whatever slip system is oriented somewhat favorably will be activated. The scaling properties of the garnet and also diopside fragment size distribution is also similar to what has been described from pulverized rocks around shallow faults, with a parallel exponent of 2 for the area distribution. So you see that although the setting and the scale at which things happen might be very different, there are similarities between shallow and deeper earthquakes, which we might take advantage of. Something else we have observed in these rocks from Bergen are these structures. The pseudotechlide would be up here. This is a branching fracture. And here we have some secondary fractures, which look extremely similar to something that is called feather features and has been, described from quartz that has been found in impact structures. And this is the first time that this is actually described in plagioclase. There are a lot of similarities also when it comes to the angle here. And these feather features are quite fascinating because they give us information about the direction of the shock wave and about the direction of the shear movement. So we have lots of different microstructures, but what do we do with it? What's the next step in our microstructural approach? We have to, of course, connect the structures we observe to processes and take into account the temporal and spatial evolution of a fault zone. Here we have an example from the Bergen arcs again, where we try to put the observed structures into an order. The fault propagates from right to left, and here around the rupture tip, fragmentation occurs. This fragmentation is concentrated on one side of the fault, which would be where the stress was tensile and not compressive. This is actually quite an important observation because it shows us that just one earthquake went through here and that this fault was not reactivated. Then shear strain is localized in the center of this damaged zone, and the rocks experience cataclasis. With further shear, these cataclasites are heated up, and frictional melting occurs. And the frictional melt is then partly injected as injection veins into the damaged zone, and it might even completely overprint the cataclasites where the pseudotechlide is thickest. And then later, and on much longer timescales, metamorphism is going to affect these rocks, which are much more fine-grained than their surroundings. This is, of course, just one particular fault, and others certainly look different. But I think it is important to really go to this level of detail if we want to understand the early processes of earthquakes. So to summarize, I addressed two main questions here. The first being how to identify intermediate depth earthquakes in rocks. Firstly, of course, by pseudotectilites, especially those that have injection veins, but also by the scaling of fault offsets and grain size distributions. And one feature which is relatively new, I believe, to this kind of rocks, but might be very important, is pulverization by crystal plastic processes. Another, the second question was how do we then understand intermediate depth earthquakes? And I think to address this question, there are two things we could focus on, and one is thin pseudotectilites, where deformation structures are more likely to be preserved, and we should focus on the damage in the wall rock. So I hope I have been able to give you some new ideas, and thank you for your attention.